Welcome. Now we're going to talk about spherical coordinates, and we're going to go through the process of deriving them because I think that will help you understand it better. Spherical coordinates represent an ordered triple point in space. So we're going to call it a point P, and we use the variables, the Greek letters rho, phi, and theta. So rho, phi, theta. So let's draw this to kind of derive what we are looking at. So we've got our coordinate system in space, x, y, and z. Spherical coordinates relate to both our definitions for polar, and then we extended polar into 3 dimensions, and that gave us cylindrical coordinates. So these all kind of go hand in hand, and part of the definitions, they're all going to play into each other, if that makes sense. So thinking about what all of these values are, we're going to imagine that we have some point up in space here in my first octant, which is P, or R, phi, theta. All right, so P is some distance, rho, out from the center. So this is not in the YZ plane. I'm going to kind of draw this a little bit more so you can see it better. So we're imagining that P is, it's shadow down into our space might be at some X, Y, 0 point, right? So we've got some point here, X, Y, 0, which we can kind of relate it in this manner, kind of a rectangle. So XY0 is its projection down into the XY plane. Now we've got this angled line coming out here. We're going to think about that being a positive rotation theta, and then we've got that measured distance r, right? So we're converting x and y into polar. So this is the same as r theta 0. And so what we have in here is we've got this little right triangle, right? And on our right triangle, we have a height here, z. So this triangle is RZ rho. So we have visualized where theta and rho come from, but where does this phi value come from? Phi is an angle rotation off of z. So rho represents the distance from the origin, this point here, we could call that O, but from O to P, our ordered triple in space. Rho is always going to be a greater than or equal to 0 value. So it's always going to be a positive or 0 value. Just like when we are dealing with r in polar coordinates, we can have a negative r, but it would go in the opposite direction. We don't want to deal with a negative rho because that would shoot down into the opposite direction as well. Phi is that angle that the segment OP creates with the z-axis. And phi can actually be a measure between 0 and pi, or 0 and 180. And lastly, theta is that positive angle rotation, considering back to using cylindrical or polar. So thinking about this image we have here and what we already know about polar coordinates and our conversions into r and theta, let's develop our Cartesian to spherical and as well cylindrical coordinate systems or units. So let's think about what we know as we relate these spherical coordinates to Cartesian, polar, and cylindrical. First thing, we know that x equals r cosine theta and y equals r sine theta, as well as the fact that r equals the root of x squared plus y squared. Now, our ordered triple needs to be rho, phi, or theta values. So we can use this theta, but what we can't use is the r. We need to get rid of the r, and we need to determine a way to define r in terms of rho and potentially phi. What I'm going to do is I'm going to resketch this rectangular plane down here for us. So here I've sketched that triangle RZ rho in a plane. And we want to, again, think about relating R to rho and phi. We don't want a Z in there. Well, one thing I know is that this little angle up here would also be phi. So let's use a trig identity to define R. Now, if we note here that R is opposite and rho is adjacent, we can say that sine of phi would be opposite over adjacent, R over rho, which allows me to rewrite this and say that R would then be rho sine phi. Knowing this is going to allow me to redefine x and y. So I can plug rho sine phi in for both of the R values, and I'll end up with x equals rho sine phi cosine theta, and y equals rho sine phi sine theta. And then z, how can I relate z from this triangle? You'll notice that z is adjacent to the angle of consideration phi, so we can say that z is going to be rho cosine phi. All right, let's think about how we can define this rho value as well. So normally we would have some r defined in terms of x and y, but we need to know how to define that hypotenuse rho. So by looking at that right triangle, we can see rho equals the square root of r squared plus z squared. So that would be relating to cylindrical, because we have an r and z in cylindrical. But then if we had Cartesian, r squared is equal to x squared plus y squared. So then we'll have plus z squared. So these are the formulas we need to know or to be able to use to relate Cartesian, polar, cylindrical, and spherical coordinate systems. Let's do one example where we convert rectangular into spherical, or I should say Cartesian into spherical. In this example, we are given a sphere with the center at 0, 0, 1. So it's a sphere of radius 1 centered at the ordered triple 0, 0, 1, and that's in our rectangular or Cartesian coordinate system. And we want to find the spherical coordinate system. And spherical means that we want rho, phi, and theta. So thinking about what we just defined, well, we know what x is. X is equal to rho sine phi cosine theta. So we have that quantity squared. We know what our y value is. Y is similar. We'll have rho sine phi sine theta. So that would be also squared. And then we know what our z value is. We defined z as being rho cosine phi. So I've got rho cosine phi minus 1 squared equals 1. So I just performed all these direct substitutions. Now we just want to simplify this and clean it up. Simplifying, I've got rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Foiling the second one here, or this third term I should say, we have rho squared cosine squared phi minus 2 rho cosine phi plus 1 equals 1. Pretty easy. We'll see those 1s are going to cancel. We're going to have some nice factoring. So if you look at these first two terms, you notice we've got a cosine squared plus a sine squared. So if I factored each of these terms out as a GCF, I've got rho squared sine squared phi, and that would be times cosine squared theta plus sine squared theta, which is of course equal to 1. So I'll write what I have left. I have plus rho squared cosine squared phi minus 2 rho, and that would be cosine phi, equals 0. So again, now if we look at these two terms, you'll see that the sine squared and the cosine squared are going to cancel out. So what I have, if I factor that, I've got rho squared sine squared phi plus cosine squared phi minus 2 rho times cosine phi equals 0. This guy goes to 1. Now I've got rho squared minus 2 rho cosine phi. And that's going to be the same, equal to 0. And that will be rho squared equals 2 rho cosine phi, or rho equals 2 cosine phi. And you can see here, this is the same as that sphere oriented at 0, 0, 1 with a radius of 1. And so in this video, we took Cartesian coordinates, we converted them to spherical, and we talked about the important formulas that we need to use when we are creating this conversion. As always, email me with any comments, questions, or concerns. Good luck.